Use the element method for proving a set equals the empty set to prove each statement in 28 through 38. Assume that all sets are subsets of a universal set U. For all sets A, B, and C, A minus C intersection B minus C intersection A minus B is the empty set. So we want to show two things here. To show that two sets are equal to each other, then that means we have to show that the first set is a subset of the second set, and the second set must be a subset of the first set. That's what, by definition, what it means for two sets to be equal. Now, if you think about this conceptually, the empty set is a set of nothing. There's nothing in the empty set. So if we think about how we would prove number one, we have to start with an element in the first set and then prove that that element is in the second set. This is an if-then statement. So the way we're going to do this is a little bit different. We're still going to start with an x that's in the first set here. And we can show that x is also an element of the empty set, but that would be a fruitless effort because the empty set doesn't have any elements. And so we can't really show that x is an element of the empty set here. So we have to prove this a different way. Instead, we're going to show that simply asserting this claim will lead to a contradiction, meaning that simply asserting the fact that this has an element to begin with is going to lead to a contradiction, which would mean that this set doesn't have any elements. But if we think about number one is an if-then statement. If an element is in the first set, then the element is in the second set. But what we're going to show instead is that by asserting the premise here to be true, we're going to run into a contradiction that leads to showing that the premise must be false. Now, if you consider the implication is actually true when the premise is false. So we're going to start by showing that the premise here will always be false. And because the premise is always false, then the implication itself would actually be true. So the way we're going to show number one is very different than the way we normally show a set as a subset of another set. So we start by letting this x be an element of this set. And we're going to run into a contradiction by showing that x doesn't actually exist. What we can do is we can unpack these intersection operations. Now, I always say work from the outside in, but in this case, these intersection operations can be done in either order. So we can unpack both of them at the same time if we wanted to here. So by definition of intersection, x is an element of a minus c, and x is an element of b minus c, and x is an element of a minus b. Next, we can unpack what the set minus means by definition. By definition of set minus, x is an element of A and x is not an element of C, and x is an element of B and x is not an element of C, and x is an element of A and x is not an element of B. Now, the key to our contradiction is that x is an element of B and x is not an element of B. And that's the contradiction here. That's the P and not P. But what does this contradict? This contradicts the very idea that there is this x in the set. Keep in mind that x was arbitrary. We don't even know what x is, but it doesn't even matter that we don't know what it is. We can still prove that it can't actually be in the set and that it doesn't actually exist. And so therefore, number one is true. Now let's prove number two, that the empty set is a subset. But I should mention that the empty set is a subset of every set. Now, we haven't discussed why that is yet, but the reason is pretty much the same as the reason for part one. And that is that number two here is an implication, an if-then statement. But the very idea that we would let x be an element of the empty set would lead to a contradiction immediately, because the empty set doesn't have any elements. And so the idea of letting x be an element of the empty set is just a contradiction by definition of what the empty set is. And so number two is also vacuously true because the premise of the implication is false. And so it doesn't matter whether or not x is an element of this other set or not. We don't have to worry about that because the implication is vacuously true. And that proves number 29. Thanks, everyone, and I'll see you in the next video.